Welcome to this session. In this session, we are going to demonstrate how to find a real valued fundamental solution of the equation x dot equals to a x. And it happens that in this case, our A matrix is a 2 by 2 matrix whose elements are 2, 3, minus 3, 2. So let's illustrate how we solve this. Solution. Here, A is given by 2, 3, minus 3, and then 2. So the first step you do is to find the eigenvalues, and the next will be eigenvectors. So first, you obtain eigenvalues of A. So, and to obtain eigenvalues of A, we need to solve the equation. The determinant of A minus lambda I is given by 0, i.e. determinant of 2 minus lambda, this will give us 0. So this 2 by 2 determinant will be 2 minus lambda, 2 minus lambda, minus minus is plus, equals to 0. Open this, so we'll have 4 minus 2 lambda minus 2 lambda plus lambda squared plus 9 equals to 0. So rearranging, we'll have lambda squared minus 4 lambda plus 13 is equals to 0. Now this results into a quadratic equation. So let's use quadratic formula to find the root to this equation. So lambda minus b plus or minus so our b here, our a is 1, our b is minus 4, and our c is 13. So minus b will give us positive 4, plus or minus square root. B squared is 16, minus, so when you say 4 times 1 times 13, you get 52. You divide this by 2 times 1 is just 2. 16 minus 52, you get minus 36. So it tells us that we'll have a complex root. So lambda will be 4 plus or minus root minus 36 over 2. Root of minus 36 is 6i, it's a complex number, over 2. So therefore, our lambda is 2 plus or minus 3i. So those are the two values of lambda. So which means that you can say lambda 1 is 2 plus 3i, and lambda 2 is given by 2 minus 3i. Now, when you have complex eigenvalues, to work out for the, if you're doing a case of a 2 by 2 matrix and you have complex eigenvalues, working out for eigenvector is easy because we just do one step. The conjugate root will actually be, when you find the solution to the same, will be a scalar multiple of the same eigenvector. So you don't have to do it twice, as in the case when you have two distinct real roots. So next, eigenvectors. So pick lambda to be the first lambda 2 plus 3i. And we know for us to get eigenvectors, so we have to ensure that this equation is satisfied. Let me pick my eigenvector. Let me use letter U. So we have to ensure that AU is the same as lambda U, where since we have our A to be a 2 by 2 matrix, U is of this form, U1, U2 is the eigenvector. So therefore now we'll say our A matrix is 2, 3, minus 3, 2. You multiply by the vector U, which is U1, U2. You should get lambda, which is 2 plus 3i. You multiply by the same vector, U1, U2. So let's evaluate this equation. You have 2u1 plus 3u2 minus 3u1 plus 2u2 is equals to 2u1 plus 3u1i, 2u2 plus 3u2i. I've simply multiplied this by every element in this vector. The implication of this equality is that the first row and the second row should actually correspond on either side. So that is 2u1 plus 3u2 should be 2u1 plus 3u1i minus 3u1 plus 2u2 should be 2u2 plus 3u2i. You see, if you call this one equation 1 and you call this one equation 2, then from equation 1, this and this are common. So it's like I have 3u2 equals to 3u1i, or in the same language as saying u2 is the same as u1i. And you should find that also if you cross this and this, these two equations should be the same. Also, from equation 2, we have negative 3u1 equals to 3u2i, and you should get that u2 is still u1i. These two equations are equal or are the same. So if I call this one equation 3, then I can say from equation 3, let u1 be a real number t, which is non-zero. So which tells me that my vector u will be given by u1, u2, which is the same as, where there's u1 I put t, u2, immediately you say u1 is t, then u2 will be t I, because u2 is u1 times I. And then you can write this one as t0 plus 0 ti. Reason as to why I'm doing this one is to separate real parts and imaginary parts. So which can be written as 1, 0 t plus, I factor out I here, 0, 1 and then I factor out t outside here. Then I say, this is my vector u. So for simplicity, letting t to be 1, then my u vector will be given by 1, 0 plus I 0, 1. If you remember well in our discussion, the introduction of this part, vector eigenvalues method, this is what we call the V, and this is what we call the W. So the solution is u e raised power lambda t. This by definition. That's this how we write our solution. So this is the same thing as saying e raised power lambda. In this case, we picked to be 2 plus 3i. 2 plus 3i times t, and then you multiply by the vector u. So which is the same thing as writing e raised power 2t e raised power 3ti, but you write it as 1, 0 plus I times this is 0, 1. From Euler's identity, e raised power theta I is given by cosine of theta plus I sin theta. So which means that e raised power 3ti is the same as cosine of 3t plus I sin of 3t. So we will write this one as e raised power 2t times, instead of writing this one, we'll have cosine of 3t plus I sin 3t, and then you multiply by the vector 1, 0 plus I 0, 1. So let's just now carry out the multiplication. So e raised power 2t. So this times this vector here will have cos of 3t plus I sin 3t. Because this is 0, so I times 0 is 0 times this one is 0. So this is only the upper element. The lower element will have this by this. Okay, let me just do step by step. This by, so this will be 0. And then plus I into this term times 0 is 0. This term times 1, we get cosine of 3t plus I sin 3t. So that's what you have. And then if I add these two vectors, I'll have e raised power 2t into, now this will be cos of 3t plus I sin 3t, 0. Let me multiply I by every element in this part, this vector. So I times 0 is 0. I times cos 3t is I cos 3t. I times I is minus 1. So I write that term first. So minus sin 3t, then plus I cosine of 3t. Then I close. So this will be now adding these two vectors, I'll have e raised power 2t into now cosine of 3t plus I sin 3t. 0 plus this will give me minus sin 3t plus I cosine of 3t. And then I can separate imaginary and real parts in this vector. So I write e raised power 2t into, so this first one, we have cosine of 3t, this one minus sine of 3t, and then plus, I factor out I, and then write sine 3t, and then cosine of 3t. So multiplying by the e raised power 2t, I'll get e raised power 2t is times cosine of 3t, and then minus sine of 3t plus I e raised power 2t times sine 3t cosine of 3t. So the real part is what is called x1, and the imaginary part is what is called x2. So e raised power 2t. So this term here, this part is what we call x1 of t. This other part is what we call x2 of t. And by superposition principle, the solution of the equation is the linear combination of these two sub-solutions. So by superposition principle, the solution x of t is given by C1 x1 of t plus C2 x2 of t, which will be given by e raised power, so C1 e raised power 2t into, so you have cos 3t minus sine 3t plus C2 e raised power 2t into sine cos, so sine 3t, and then cosine of 3t. So this is the general solution of that given equation. So that's how we solve this given differential equation. Thank you.